So we're going to call this example 3.2.1, and we'll call this an incidence matrix. Okay? And we're going to call this U1. We're going to call that U2. We're going to call that U3. We're going to call that U4. We're going to call that U5, and we'll call this edge 1, edge 2, edge 3, edge 4. Anybody see something that's quite interesting?
There's one less edge than.
Okay, have you seen something that looks like this? And what if I were to just go like this? Dunk! Oh, really? I don't see any masses or springs here. What are you talking about? You know what you're doing now, right? It's called applied math modeling. You're seeing stuff that's not there, right? Most people would go to a psychiatrist for that. We would go to the bank for that, right? So let's go ahead and do this. I'm right with you, Wesley. I see that too. So now we go U1, U2, U3, U4, U5. Let's go ahead and just do a directed graph on that sucker. Do you remember what the way that we filled that one in? Be careful. When we said that an edge comes out, is it adding to the system or taking away from the system? Adding to, which means it's a positive. When it goes in, it's taking away from the system as a way to kind of think about it. What is it? Negative. Everything else gets 0. So now what?
0, 1, -1.
Yeah, and then what I might do is just edge 3 connects U3 and U4. Out of U3 into node 4, the rest of them get 0. Edge 4. Out of U4 into U5, all the rest of them get 0. What's the corresponding incidence matrix associated with this particular digraph? This is going to show up later in the course, so hint, hint. So here we go. A would be equal to 1, -1, 0, 0, 0, 0, 1, -1, 0, 0, 0, 0, 1, -1, 0, and then 0, 0, 0, 1, -1. What would we say about this thing? From a class, is it square? Is it tall and narrow? It is short and wide. What if I wanted to turn it into a tall and narrow matrix? Transpose it. Okay. So. Yeah, I think we've already talked about this. I'm going to go ahead and just give a call out right now. This is definitely, I'm going to call this for now an Anderson thing, just so that I don't get you in trouble. These subscripts track dimensions. And I actually like to put subscripts on my matrices, but make sure they're subscripts, not what? These are not superscripts. And the reason that I like to do this is, so in a problem like A times X equal to B, which we're going to see a lot in this class, one thing that I'm going to claim is please use subscripts to specifically identify dimensions for yourself. And we've talked about this beforehand, but this is part of the anatomy of matrices. Behind every symbol is a set of how many real numbers? M times N. In this case, how many real numbers? 20. When I just write the symbols, this is one of the most powerful things about linear algebra. It allows us to suppress all of those details. But the problem is many young students never actually, what is it called if you never actually know the details to begin with? It's not suppression. Blissful ignorance, I suppose, right? And the problem with blissful ignorance is you can get yourself in a lot of trouble, right? You can wind up in a position where you're multiplying matrices where the inner dimensions don't agree. You can write ridiculous stuff on the page, and none of that relates to the actual math underneath. And so my claim is one of the parts of identifying dimensions, of identifying the anatomy of matrices is explicitly writing the dimensions as subscripts. I saw probably at least 10 people on the test put these in the superscript, which I've never done. And so I'm going to say today, when you write dimensions, where do I want them? Subscript. And if you really like to, you could write a little box around them to represent that you're doing this. This is non-standard in the field. If you wrote notes to another linear algebraist, they'd be like, why are you doing that for me? I already do that for myself. But for just students that are novices, that are not used to working with matrices 20 hours a week or 30 hours a week, I'd like you to get in that habit.